So a farmer is trying to develop a deterrent to keep birds from eating his crops. He plans to conduct an experiment using garlic oil to study the effectiveness of an environmentally friendly bird repellent. Better than poison. The experiment will use starlings, a bird species that often damages corn crops. Food granules made from corn are to be infused with garlic oil in each of 5 concentrations. Ooh, 5 concentrations. We've got 0%, 2%, 10%, 25%, and 50%. The farmer will determine the reaction of the birds by measuring the number. Oh, so this is what we're going to measure: the number of food granules consumed during a 1 hour period following the overnight food deprivation. So we're going to starve them and then offer them food that they hopefully won't like. There are 50 birds available for the experiment. All right, we're doing an experiment. Is this graded? No, just by you. You're grading this. I don't have any control over your grades at this point. I've already submitted your grades, but I'm glad more of you are showing up here. The farmer will use 10 birds for each concentration of garlic. Each bird will be kept in a separate cage and provided with the same number of food granules. So for the experiment, identify the treatments, the experimental units, the response that was measured. So the treatments are the 5 concentrations of garlic. All right, and you probably want to list them 0%, 2%, 10%, 25%, and 50%. Right? 1, 2, 3, 4, 5. No, you do not have to say 5. You could just say these percents. I think they were looking for the word garlic or concentrations of garlic somewhere, some sort of context. All right, the experimental units are the 50 birds. All right. If you want to be specific and say that they are starlings, that's cool too. All right. The response that will be measured, we are measuring the number of food granules consumed. Food granules consumed. I don't know exactly what they're referring to as a granule, but you know what? Whatever. You can write the rest of this too. During a 1 hour period following overnight food deprivation, you can write that too, but all we needed was food granules consumed. And that is our response that we're going to measure. All right, so grading that, and I'm going to add attendance here for a couple. Non-Amy and Anaya. Getting closer to the 20 I was hoping for. All right, so the treatments are the different concentrations of garlic oil. So notice it doesn't say 5, it just says the different concentrations, and it lists them 0, 2, 10, 25, and 50. So those should be listed somewhere. I think if you just said the different concentrations of garlic oil, that was enough. But I mean, it's the AP exam. You can list the 5 numbers and make sure you get a 5, you know. Experimental units are the birds. The response is the number of food granules consumed. If you got all 3 of that, that is an E for part A. If you only had 2 of them, that is a P. Anything else is an I, no points. Part B here. So after performing the experiment, the farmer recorded the data as shown in the table below. So for each concentration, there is the number of granules consumed. The 10 birds here is irrelevant. Like, we're not using that for anything. These are the numbers that we are looking at. All right, construct a graph of the data that could be used to investigate the appropriateness of a linear regression model for analyzing the results of the experiment. All right, so that means we have an X and Y axis, and we've got to label them and say what they stand for. If you did not label them, bad. All right, so 0 is going to be there in the corner, 0, 0. And so we are measuring the number of food granules consumed. So that's what we want over here. And in fact, it's the mean number of food granules consumed. And on the x-axis here, we're going with the garlic oil concentration. That's our other variable, garlic oil concentration. All right, so this is our explanatory variable down here, and this is our response variable over here. You don't have to label explanatory and response. Remember, explanatory is the X and the response variable is the Y. All right, so let's see. The number of granules consumed. We need to go up to at least 58. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to do it. All right, so we have some choices. If we count by 5, it's not going to make it. All right, because we only get to 50. So we could count by 10 or we could count by something else. It's kind of up to you what you want to count by. I'm going to go ahead and do just 10. The hell with it. 20, 30, 40, 50, 60. And that's all we need to go up to. If you got cutesy and wanted to go up to like, wanted to count by like 7 or something like that, or 8, or, something that would get you to 58, that's fine. You can do that. Not a problem. All right. On the x-axis, we need to go from 0 to 50. I'm going to go ahead and just count by 5s. So let's see. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. I probably could have skipped out a little bit more if I wanted to, but you know what? This is going to work. So we got 0, 58 as a point. So 0, 58, we're up here. All right, 2, 48. So we're not going over much, and we're dropping down somewhere around there. These points do not have to be exact, by the way. As long as they're close, you're good. 10, 29, 10, and we're up here at about 29. That's going to disappear on me, isn't it? There we go. 25, 24. Right, there we go. And 50, 20, 50, 20. All right. And I don't even think you needed to go down to 0. Like you could have started at like 10 or 20 if you wanted to and counted up. That would work fine too. All right. Now, so there's our graph of these points. Based on your graph, do you think a linear regression model is appropriate? Explain. So does this look like they're lining up as a straight line, or does it look like they're doing something else, basically, is what it's asking. I think it's doing something else. I think it looks like it's exponential decay. All right. So I would say this does not look linear. It looks like exponential. All right, let's see what they said. All right, so we need to label the axis, the concentration, and the mean number of food. They went from 20 to 60, good for them, and from 0 to 50. All right, that's fine. It doesn't really matter as long as you had something labeled here, and at least 3 numbers labeled is usually the minimum you need on an axis. But go ahead and just count by something. All right, so we got a correct scatter plot. So we had points that were basically following that pattern. Yep. We got the axes labeled and scales. Yep. Did we conclude the graph is not linear? So let's see. The curve pattern of the scatter plot reveals that the linear regression model would not be appropriate for the relationship between these variables. Yeah, we said it wasn't linear. It looked like it was exponentially decreasing. Either way, you could just say, well, it looks like it's curved and not straight. So not linear. All right. We could model this with a line. It just would not be a good approximation. All right, so if you messed up something if you have the correct graph and the wrong conclusion, that's a P, or you have something messed up on your graph, like you forgot to label something, but you still have the correct conclusion saying that it would not be linear, that would also be a P. All right, and that's it for grading this one. So it was just the 2 parts. All right, so each E was worth 2 points, each P is worth 1 point. The second one, and again, if you have questions, throw them in the chat whenever, or interrupt, that's fine. So number 2 here, and by the way, these were both past AP questions. They were on AP exams in the past. So a radio station plays 35 pop songs during a 3-hour show. The program director at the station needs to know the total amount of airtime for the 35 songs so that time can be programmed for commercials and news. The distribution of the lengths of pop songs in minutes is roughly symmetric, with mean 3.4 minutes and standard deviation 0.9 minutes. Describe the sampling distribution of the sample mean song lengths for a random sample or for random samples of 35 songs. So now we're working with a sampling distribution. So that means our N here is 35. The mean of the sampling distribution will be the mean overall, which is 3.4. And the standard deviation for the sampling distribution will be the standard deviation here divided by the square root of n, which is 35. So I want to say that it told me to describe a distribution. So I'm going to cuss the mean song time is 3.4 minutes. Now I've got context and I've got the center, mean, nothing unusual. In fact, that's not going to be checked here, but on other graphs or other questions, it could be. Shape. Let's see, our n here is 35. So n equals 35 is greater than 30. So by the central limit theorem, it will be normal, or approximately normal. I should probably say approximately. Nothing's ever exactly normal. It's usually just approximately normal. And then spread, our standard deviation for the sampling distribution here is 0.9 over the square root of 35, which is 0.1 something, I think. 0.152, there we go. And that is also in minutes. All right, so that's part A. Part B, if the program director schedules 57.5 minutes of commercials, okay, not songs, for the 3-hour or 180-minute show, only 122.5 minutes are available for music. So that's what we're talking about. Don't care about this. Approximately, what is the probability that the total amount of time needed to play 35 randomly selected songs exceeds the availability or the available airtime? All right, so there's two ways we can do this. We can scale everything up to the total amount of minutes, or we can scale everything down to the individual song level. So the answer that they provide is they take this 122.5 and divide it by 35 songs. And that gives us, what does that give us? 3.5 exactly. That was nice how that works out. So that works out to 3.5 minutes per song. All right, well, we said we have a normal distribution. We said our mean was, what did we say, 3.4? Our standard deviation was 0.152 because it's a sampling distribution. And 3.5 would be up here above it. And we want to know what's the probability that we're going to exceed. So big greater than 3.5. So there's our distribution. To find that area, we would just use normal CDF. Our lower bound would be the 3.5. Our upper bound would just be something big. Our mean is 3.4. And our standard deviation was the 0.125 or 152, sorry, 152. And we just throw that in the calculator, and I think it was 0.25, 0.255, yeah. All right, and that's how we do that, by scaling it down. Scaling it up is a much harder problem, and most people get it wrong if they scaled it up. So to scale it up, we would take this standard deviation here, this 0.09, or 0.9, sorry. And we would want to find its variance, so we'd have to square it. And we'd have to add it up together 35 times, right? So remember, like the standard deviation for the combined distribution, like A plus B is like the standard deviation of A squared plus the standard deviation of B squared, like the Pythagorean theorem stuff. Yeah, well, that's what I'm going over right now, son. So if you use the 122.5 as your lower bound, you'd have to scale up the mean and you'd have to scale up the standard deviation. The mean's not so hard. The mean would be scaled up using just 3.4 times the 35 songs, and that would be our new mean. But the standard deviation, we'd have to use this, and we'd have to technically do it 35 times. So what you would end up getting is that the standard deviation would be equal, or the standard deviation squared would be 35 times 0.9 squared. And then we take the square root here. So we'd end up getting the standard deviation is 0.9 times the square root of 35. And that's what everybody gets wrong, is they don't have that square root of 35. All right, but yeah, you could scale up, in which case, let's see, I'll use a different color. In which case the lower bound would be 122.5. The upper bound would still be something very big. Our mean would be 3.4 times 35, and our standard deviation would be 0.9 times the square root of 35. And that would give us the same probability, if you are wondering. All right. But most people that got this right did it this way. They scaled down instead of scaling up, scaled down to the per song level. All right, so the first one, all you needed was the center, the shape, and the spread. Why do you have to multiply by 35? Because this was the time for one song, and we were doing 35 songs in that time frame. So we want to know the total average time that it would take to play all 35 songs, because if we're using this as our lower bound, that means we're working with the total amount of time from all the songs, because that's the total amount of time for all the songs. If we're using this, that means we're working with just the one song at a time average. I know. I did it the other way the first time I did it. I went up, and then everybody in the room was like, no, you want to go down, because you get the standard deviation wrong. If you go up, everybody forgets the square root of 35 part. All right, so for the first one, the center, 3.4 is the mean. Shape, normal by CLT. That's what we were looking for. And spread, the standard deviation is, honestly, that was enough. Calculations required. Or maybe they wanted that, actually. Okay. And if you have 2 of the 3, that got you a P. If you said nothing unusual, that's fine. It wasn't needed for this one. They didn't care. All right. And there's the second one, grading. So we had to say it was normal somewhere. If we said normal CDF, that takes care of that part. We have the correct bounds. So if you drew it, more power to you. If you didn't draw it, as long as you labeled everything in here, that's the correct bounds, the correct mean, and the correct standard deviation. And then you needed to have the answer somewhere. There it is. So if you write out normal CDF with all the parts labeled and the answer, that can get you full credit. If you draw the graph and then do all the work, that's fine too. In fact, this is kind of missing that it's normal. So you'd want to have an N 3.4 comma 0.152 somewhere. I think they said it was okay as long as you said it was normal in part A. Yeah, it was fine. All right. If you messed up one of the things, so it finds normal probability with the wrong standard deviation, unless they use the same wrong standard deviation from part A, then that's a P. If you use the same wrong standard deviation in part A, you're fine. Yeah, you get an E if you use the wrong standard deviation from part A. All right, and that's me explaining it how it worked the other way. So yeah, if you did the 3 times, or the 35 times the 3.4, you get 119, and that would be the square root. That's the 0.9 times the square root of 35. So that would be the other way to do it. I mean, you still get the same exact answer. All right. So the scoring of that, again, each E was worth 2 points. Each P was worth 1 point. All right. So hopefully that wasn't too bad. Hopefully you at least took a shot at it and tried it. So that is the kind of question that you can get points on that. You might not get all the points, but you get points. And by the way, you don't have to submit this on Google Classroom. I'm not checking your stuff on Google Classroom to see if it's right or wrong. Someone that was here just submitted, who's not here anymore. All right. Teach his own. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 questions or so that we got about half wrong here that I'd like to at least take a look at. All right. So the first one, a lot of these are just definitions, so it's not going to be a lot of calculations. So this was from parts A, I believe. I think I have them in order. So the manager of a city recreation center wants to estimate the percent of residents who favor a proposal to build a new dog park. To gather data, the manager will select a random sample of city residents. Which of the following is the most appropriate interval for the manager to use for such an estimate? All right, the percent of residents. All right, so that means we're doing our interval for proportion. We're only taking one sample. All right, we're just asking one sample of people what they feel about things. So it's definitely a one sample, not a two sample. All right, we are working with proportion. All right, we are never finding intervals to estimate sample proportions. All right, intervals estimate population information. They don't estimate sample information. Sample information is what you actually get for your p-hat. That's what you get from the data. All right, what we're estimating is the population proportion. Since it is with p, zapped tax isn't applying here. We're using z. Z goes with p. All right, so that's that one. Moving right along. Biologists studying horseshoe crabs want to estimate the percent, that's a P, of crabs in a certain area that are longer than 35 centimeters. The biologists will select a random sample of crabs to measure. You guys know what horseshoe crabs look like? I don't know if you guys would or not. Right. Which of the following is the most appropriate method to use for such an estimate? So we've got a one sample Z interval for population for proportion. Yeah, so we're taking one sample of crabs. We're looking for percent, so that's a proportion. So it's definitely population proportion, not sample proportion, right? And it's just one sample, so it's not these two sample guys down here. And it is Z because we're working with proportion. Man, why don't we go with one sample for sample proportion? Yeah, we're never estimating the sample proportion, guys. We can find exactly the sample proportion. No reason to make an interval for that. We use it to make the interval, but it's a population proportion. That's the true proportion that we're talking about. When we use the word true, that's what we're talking about. All right, next one. A town council wants to estimate the proportion of residents who are in favor of a proposal to upgrade the computers in the town library. A random sample of 100 residents is selected, and 97 of those selected indicated that they were in favor of the proposal. Is it appropriate to assume the sampling distribution of the sample proportion is approximately normal? All right, well, there's two conditions we got to check for normality. N times P needs to be greater than or equal to 10, and N times 1 minus P also needs to be greater than or equal to 10. And if we don't have P, we use P hat here. So our N is 100. Our P, or in this case, P hat, 97 out of 100. Which is 0.97. So N times P is 100 times 0.97, which sure enough is 97. That's definitely greater than or equal to 10. That checks out. But if we do N times 1 minus P, we get 100 times 1 minus 0.97. So that's 0.03. That gives us 3, which is less than 10. That's a problem. So the answer to their question, is it approximately normal? No, because the sample is not large enough to satisfy the normal conditions. Yeah, we need a much bigger N for that to work because the size of the population is not known. That gets us independence. This has to do with independence. Yes, because large enough? No. All right, so the CLT only applies when we are working with means, right? And we're not working with means. We're working with a proportion, percents here. Okay, so that's the big difference here, percents. No CLT allowed. All right, next one. Sue and Javier are working on a statistics project to estimate the proportion of students at their school who have a pet dog. Sue selects a random sample of 81 students from the 2,400 students at their school, and Javier selects a separate random sample of 64 students. They will both construct a 90% confidence interval for their estimates. Consider the situation in which the sample proportion from Sue's sample is equal to the sample proportions for Javier's sample. So they have the same p hat, is what we're saying. Which of the following statements correctly describes the interval? All right, so now what's happening here is her sample size is bigger than his sample size. So since her sample size is bigger, we end up with p hat and 1 minus p hat over n, and then times a z star, and then p hat plus or minus that is how we make those intervals. So the p hats will be the same. The z stars will be the same. But what's going to be different is this n. She's going to have 81 down here, and he's going to have 64 down there. All right, so that means she's dividing by a bigger number on the bottom. That means this margin of error is smaller for her. Because she's dividing by a bigger number on the bottom. So that means her interval will be smaller. All right, so let's see, Javier will be greater, have greater degree of confidence. No, it doesn't have anything to do with confidence. Suze will have a greater degree. No, they both have the same confidence level because we're both doing a 90% confidence interval. So the confidence level doesn't change. The width of Sue's interval will be the same. No. Width of Sue's interval will be wider. No, smaller. Sue's will be narrower. smaller, narrower. Yeah, that works. That's our guy right there. All right, so you got to keep these formulas in mind here, guys. I know we don't use them a lot, but you do have them there available on the formula sheets. And they do come in handy on these multiple choice questions. All right, next one. A one sample Z test for a population proportion P will be conducted. Which of the following condition checks that the sampling distribution of the sample proportion is approximately normal? Random sample? No, that means it's an unbiased estimator. All right, that means we're getting rid of bias. That has nothing to do with normality. N times P naught greater than or equal to 10 and N times 1 minus P naught greater than or equal to 10 for sample size N. Yeah, when we're doing the test, that was our condition for the normal condition. Yeah, it's time for you to go, isn't it? The sample size is less than or equal to 10%. That was independence. That's so we could use the standard deviation. So the only one that applies here is number 2. Number 2 is the one we want here. All right. And I believe, well, are we done with the first section? On to the next section? I think we're on the next section here. All right. So I read it as like if it work. Oh, for doing the test. No, it just wanted the normal condition. It was just the middle condition. That's why we always write normal after that one, because most people don't do that, right? They usually just write large counts. So a state biologist is investigating whether the proportion of frogs in a certain area that are bullfrogs has increased in the past 10 years. So we're looking for, has it increased? The proportion 10 years ago is estimated to be 0.20 from a recent random sample of 150 frogs in the area. 36 are bullfrogs. The biologist will conduct a test. They give you the null hypothesis and the alternative hypothesis. Which of the following is the test statistic for the appropriate test? All right, so you could run this test on your calculator if you wanted to, and it's just asking you, what are you going to get for Z in the end? That's all it's asking you. So you could do this test on your calculator and just get Z, and then work each one of these out and see which one of those matches that Z. All right, or you could actually do the formula for Z. So Z equals the, let's see, it's the mean. No, it's the other way around. Sorry, it's been a while since I've done this. We haven't gotten to it yet in the other semester. So it's X minus the mean over the standard deviation. All right, which in this case would be the P hat minus the actual P naught over the standard error, which uses P naught over N, like that. So our N is the 150. Our P naught, they told us, is 0.20. Our P hat is the 36 out of 150. Honestly, it might be easier just to run the test on your calculator, but this will get you there. All right. So if we work that out, I believe that is 0.24. All right. I'm just getting that because those are the only numbers listed here. So that's the only thing it could possibly be. So I'm not even working it out. I'm just looking at the numbers and saying, oh, it's got to be 0.24. So that means our Z is 0.24 X minus the mean 0.20, the given value, over the square root of P naught 0.20, 1 minus 0.20 over our sample size, 150, which, if you can read it, is that guy right there. All right, the difference in the two divided by the standard error, or the standard deviation. I guess it's standard deviation here, not standard error. All right, so that one is tricky. All right, but again, you could do this test on your calculator and just get a t value, and then just say, or Z value, sorry, Z, we're working with proportion. Just get a Z value, and then just work out and see which one of those matches it, if you don't know the formulas. All right, next one. Let's see. A hypothesis test was conducted to investigate whether the population proportion of students at a certain college went to the movie theater last weekend. I guess that's really kind of moot at this point. Is that for standard deviation? Yeah, that was for standard deviation. Is greater than 0.2. A random sample of 100 students at the college resulted in a test statistic. So there's our Z-score right there. Assuming all conditions for inference were met, which of the following is closest to the p-value of the test? All right, and we wanted to know went to the movie theater is greater than. So this is a one-sided test. and we're getting a Z. All right, now it doesn't really matter. We're working with Z-scores, and this is 2.25. So if we're working with Z-scores, that means 0 is our mean, and our standard deviation is 1. And really, it's asking what's going to be this area up here. All right, so we can just use normal CDF. The lower bound would be that Z-score, 2.25. Our upper bound would be just something big. Our mean would be 0. Our standard deviation is 1. Right? And we can just throw that in our calculator, and that gives us this for our p-value. All right, but yeah, this is tricky. It's really asking, like, do you know what's going on with the test? And then can you realize to use the 0 and 1 when we're working with Z-scores? It's putting a couple of different concepts together here. So if you missed this one, that's not, I understand. But again, 8 people got it. So 8 people figured it out. Or at least some of those 8 people figured out. Some of them probably guessed. All right. Next one, more formulas here. Oh, this one looks like they're just asking for standard deviation. All right. So in the United States, 36% of people, oh, they're giving us a percent right there, have a blood type that is A positive from a random sample of 150. There's our N. From Norway, 66%. Wow, that's a lot different. Had a blood type that was A positive. Consider a hypothesis to investigate whether the proportion of people in Norway with blood type A positive is different from that of the United States. Which of the following is the standard deviation used to calculate the test statistic? Basically, it's asking you what's the standard deviation here. All right, so the standard deviation for p hat, the sampling distribution, is the square root of p naught, 1 minus p naught over n. P naught is our null hypothesis. Our null hypothesis is that p equals 0.36. Our alternative hypothesis is different from. P is not equal to 0.36. I have a feeling we're going to end up with the alternative hypothesis if we actually did the test here, because 66% is a long ways away from 36%. I mean, even with the sample size of only 150, that's still, we'll get you something pretty big here. So we're going to use the 0.36, 1 minus 0.36 over 150. And let's see, that uses the 24, that 44. I don't know where that's going from. There's the 36, there's the 150. Hey, that looks like 1 minus 0.36. This didn't have the square roots. That also didn't have the square roots. So this is our guy right there. Just the formula for standard deviation. All right. Next one. Molly works for a meat producer, and she needs to determine whether containers of ground beef have the correct fat content. She obtains a random sample of 120 containers. There's our N, 120, of ground beef, and finds that 84%, that looks like a p hat, right, have the correct fat content. Well, that's good. Molly then conducts a hypothesis test, right, and our null hypothesis is not equal to, so that means it is a two-sided test. Calculates the test statistics, so that's Z right there, Z, with a p-value of that. Oh, they're even giving you the p-value. Which of the following represents the meaning of the p-value? Oh, the p-value meaning question. They like to ask this one. We went over it for a little bit, but we really just went, I mean, we went over it once, I think, maybe twice, and that was it, and then moved on. All right, what the p-value means is if H0 is true, the p-value is the probability of getting a sample value or sample statistic at that value, p hat in this case, or farther away. All right, you can just think about what it is under the normal curve. Like you have this normal distribution, you have your p naught here in the middle, you got your standard deviation. We find this test statistic here, and we see what, this is p hat. We say, what's the probability of being this far away or farther away? And that's our p-value. If we're doing a two-sided test, we also double it and add it over here as well. So both of those together make the p-value when we're doing two-sided, and we are doing two-sided here, which is a little weird. So it is, if the population proportion is true, which is that 0.80, it's the probability of observing a sample proportion, sample statistic in this case, sample proportion of at least 0.84, which is what we got, 0.84, that's our p hat, or at most 0.76. So that would be what happens if you go down to the other side. So like this was going up 4%, and this would be going down 4%. All right. So this would be the at least 0.84, and this would be the at most 0.76 side over here. That is tricky. Is that p-value? So if we add up those two sections, that gives us 0.273. Don't feel bad if you missed that one. All right, 2 left here, then we are done. Chicken hatcheries employ workers to determine the sex of the baby chickens. Doesn't that sound like a fun job, guys? One of you could grow up to be someone who checks the sex of baby chickens. Huh? Wouldn't that be fun? All day, every day. The hatcheries claim that the workers are correct 95% of the time. That's a pretty good correct rate. I don't know how you messed that up, though, but I don't know. Who cares? I don't know how you can tell a chicken's male or female either when it's a baby. Anyways, an investigator believes the workers' success rate, workers are correct, is actually less than 95% of the time. The investigator selects a random sample of chicks and finds the hatchery workers had a success rate of 0.936. So that's not far off. The conditions for inference were checked and verified. The p-value was given by 0.03. If the null hypothesis is true, which of the following statements is a correct interpretation of P? All right, so we're only doing the one-sided. We're only doing less than. So again, interpretation of P means if the null is true. So if the proportion is actually 0.95, the probability of getting this number that we got or farther away, in this case lower, less, would be this p-value, 0.03. So of all possible samples of the same size, 3.22% of the results will result in a success rate of that much or less. Yeah, that's what it works out to. That's another way of saying it. But yeah, so if you have, again, you get a sampling distribution, the 0.95, they're saying if that is true, the probability that you would get a sample down here at 0.936 is 0.0322, because there are samples that happen that would have a mean down here. That is possible. So of all possible samples, because it is a sampling distribution of the same size, well, yeah, sampling distribution is for just one particular size. 3.22%, that's that p-value, will result in a success rate of that much or less. Yeah, usually we end up saying, you know what, it's not just not likely we'll end up this far down because that's less than 5%. But in this case, they want us to interpret it and not actually come up with a conclusion. All right, last one. Is the significance level of a hypothesis test equivalent to the probability that the null hypothesis is true? What does that even mean? No, actually, it's quite the opposite. So like, let's just say we have some sort of null hypothesis that P equals P naught. And let's just say our alternative is one direction, that P is actually greater than P naught. Haha, one direction, it's a band. P naught, and we get, so if we're doing a test with an alpha value of like 0.5, that's our significance level, then this area here, it might be a little bit bigger than that, is 0.05. That's our alpha, our significance level. All right, if we end up getting a p hat somewhere out here, that's when we're rejecting. If we get a p hat somewhere back here, that's when we fail to reject. So the significance level is the probability of rejecting the null hypothesis when the null hypothesis is actually true. Yeah, that's actually what it is. All right, it's the probability of ending up here in this rejection region if P naught is actually true. All right, the significance level probability of rejecting the null hypothesis when the null is actually false. No, that's not what it means. When the null hypothesis failing to reject. No, it's not failing to reject. That's like the different types of errors. The significance level is the probability that the null hypothesis is actually false. No, that's not what it is. All right. So yep, that's the one right there, the top one. I know it's kind of a tricky, wordy definition there, but that is what it works out to be. And that is all of them. Whew. Got through them all.